Thank you for the introduction. I'm Yuepeng Wang from UT Austin. I'll be talking about verifying equivalence of database-driven applications. This is joint work with Isil Dillig, Shuvendu Lahiri, and William Cook. Imagine you are writing a web application that interacts with a database, and you would like to refactor the underlying schema for performance or maintainability reasons. You have to change the program as well because it's broken. After spending many hours doing these changes, you may start to wonder if you have introduced a bug. If you have ever found yourself in the situation that I just described, you are actually not alone. In fact, schema refactoring for database applications is so common but difficult that there are several textbooks written on this topic. These textbooks also point out that database applications are difficult ground for refactoring, and testing the validity of a change may be difficult. So the goal of this project is to automatically verify equivalence of two database programs in the presence of schema changes. Furthermore, we want the technique to handle complex refactorings where the developers can change the structure of the schema. For instance, some examples of structural schema changes include splitting a table into multiple ones, or merging multiple tables into a single one, or moving columns from one table to another. More concretely, let's look at an example that I found in a real-world application called CDX. The application has a table called subscriber in the original schema, which has three columns: SID, SName, and filter. Since the filter column stores a huge JSON object and it may potentially slow down some queries, the developers decide to move this column into a separate table. And to preserve the correspondence, they add a foreign key in the subscriber table. So after the developers change the schema, they also need to re-implement the program. For example, suppose you have three transactions in the program: one for creating a subscriber, one for updating the subscriber information, and one for querying the filter. Under the new schema, the interfaces of these three transactions remain the same, but all their implementations are different. For instance, this creation transaction previously just insert a subscriber record into a single table, but now it has to insert two separate records into different tables. For other transactions, you also need to do similar modifications. Now that you have some idea about the problem that we try to solve, let me talk about the key challenges. The first question is, what does this even mean for two database applications with different schemas to be equivalent? Since there is no existing definition, we have to formalize what we mean by equivalence in this context. Once we define the equivalence, we then need a methodology to prove this properly. That is, if I give you two database applications, how can you prove them equivalent? Finally, since we want our technique to be push button, we have to come up with an algorithm to automatically verify the correctness. In other words, we want to provide complete proof automation. Now let me talk about how we solve these challenges one by one, starting with the formalization of equivalence. Our definition is inspired by the behavioral equivalence of two general systems, which basically means that if you do same actions on both systems, you can always observe the same behavior, no matter what is the internal representation of the system. Now, in the context of database-driven applications, the system is a database instance under a certain schema, and the actions correspond to update transactions. Observations are results of query transactions. Intuitively, if two database applications are equivalent, no matter, you can always observe the same query result as long as you apply the same sequence of updates on both programs. Formally, let's consider two applications P and P prime that have disjoint set of variables. In the remainder of the talk, we will just assume P and P prime have same interfaces for update and query transactions, but the underlying implementation of those transactions may be completely different. We say P and P prime are equivalent if and only if for any sequence of updates U and for any query Q, you running the query queue after doing all the updates in U on both applications yield the same result. Going back to our running example, the equivalence of P and P prime means that if I execute an arbitrary sequence of create subscriber and update subscriber transactions, the getSub filter should always return the same result. Now we have defined what it means for two applications to be equivalent. Then let me talk about how can we prove the equivalence. First, since there are infinitely many possible update sequences, it's not feasible to verify the equivalence by checking this update sequence individually. So we develop an invariant-based approach. The key idea is to find a so-called bisimulation invariant that tries to correlate the database states of these two systems. However, we don't want any bisimulation invariant. In order for us to verify the correctness of this invariant, it must be inductive. In other words, the invariant should be preserved after performing corresponding updates on both programs. And furthermore, for the invariant to be useful, it must be sufficient to show the equivalence. That is, if the invariant should be strong enough to show that for any pair of corresponding queries on both applications, these queries can always generate the same result. So to recap, our strategy for proving equivalence in this context is to find an inductive bisimulation invariant that is strong enough to imply identical query results. And in the paper, we have proved that this methodology is sound and relatively complete. That means if two database applications are equivalent, you can always prove this by finding a suitable inductive bisimulation invariant. I want to talk more about the bisimulation invariant. Suppose you have an invariant phi that holds initially with empty databases. Then consider a pair of updates UI and UI prime with arguments x and y. Then we say the invariant is inductive with respect to these updates if the whole triple is valid. Basically, the whole triple just says that assume we know the invariant in the beginning, and we know the arguments x and y are equal. After we execute UI and UI prime, the invariant should still hold in the post state. And similarly, consider a pair of queries QI and QI prime with arguments x and y. We say the invariant is sufficient with respect to these two queries if the logical entailment holds. The logical entailment essentially says that assume we know the invariant in the beginning and we know the arguments are equal, then the query results of QI and QI prime are the same. It's pretty straightforward. Then now you should know how to prove the equivalence manually. So our next step is to automate this process. To to automate the equivalence proof, there are two main challenges to consider. The first one is that given a candidate bisimulation invariant, how can we automatically verify it is indeed inductive and sufficient? The second is that since there is no existing oracle that can generate this kind of invariants, we need to build our own tool to automatically generate the invariant candidates. Let's look at this one by one. Given a candidate bisimulation invariant phi, we want to check if it's strong enough to show the equivalence. Towards this goal, we develop a theory called theory of relational algebra with updates, or TRA for short, to encode the constraints and transactions we encounter in the program. Then we schematize this theory using theory for lists, so that an SMT solver can automatically reason about it. Then the sufficiency checking boils down to checking this logical formula is TRA valid. Also, consider the candidate invariant phi. We need to check if it's indeed inductive. Otherwise, we don't know if it's a valid invariant. So similar to sufficiency checking, we also use the same first-order theory to encode the constraints and transactions. But in addition to that, we develop a strongest post-condition semantics of all the update operators. Then the validity checking of this whole triple boils down to checking this formula that involves the strongest post-condition is TRA valid using SMT solvers. So now we know how to prove the correctness of an invariant. Let's talk about how to automatically synthesize them. The key idea is to perform a fixed point computation to find the strongest conjunction over a predicate universe that corresponds to a bisimulation invariant. In our case, all atomic predicates in this universe are obtained through template instantiation. Specifically, we have identified a set of templates that are useful for proving equivalence in our scenario. For example, the ones listed here. And then we instantiate these holes with concrete table names and column names in the schemas. Then you get a whole bunch of atomic predicates. Put everything together, the entire verification workflow looks like this. In the beginning, we generate the predicate universe by template instantiation, and say, let's call the universe P. Then we check if the conjunction of every predicate in P is sufficient or not. If it's not sufficient, we directly conclude that we cannot verify the equivalence because this is the strongest possible invariant candidate. Otherwise, we still need to check the inductiveness. If it's indeed inductive, then that means we have already found a bisimulation invariant that is both sufficient and inductive, which means the equivalence of these two applications is successfully verified. If the invariant is not inductive, we have to weaken it by removing predicate from the universe one by one until we reach a point that we can get the conclusion. Note that this procedure is guaranteed to terminate because the number of atomic predicates in P is bounded, and we will remove one predicate from P in each iteration. So far, we have learned how to prove equivalence, or how to automatically prove equivalence of two database applications. You may wonder if the technique is useful in practice because the developers may introduce some new features during the schema refactoring. Let me illustrate this with a simple example. Consider again the motivating example. Suppose the developer wants to add a new column, say email, while splitting the subscriber table. Now, the new transactions may use more tables and columns, but the new results of query should include the old query results to make sure no information is lost. To help the developer prove this kind of refactoring is also correct, we introduce a notion of refinement for database applications. The proof methodology for refinement is similar to those for equivalence. As before, we also try to find an invariant that is both inductive and sufficient. However, the definitions of inductiveness and sufficiency are slightly different. So it's worthwhile to point out that we carefully modify the sufficiency definition so that we can capture the requirement that new results should include the old results by introducing an additional projection operator. In particular, it means that the refinement relation just requires the old result is a projection of the new result. And this concludes the technical part of this presentation. To evaluate the effectiveness and efficiency of our proposed technique, we have implemented a research prototype called Mediator and evaluated by performing two sets of experiments. First, we evaluate Mediator on challenging schema refactoring examples from the textbooks. And second, we evaluate Mediator on real-world web applications from GitHub. Let's look at the first experiment. We collected 8 benchmarks from this book, Refactoring Databases, Evolutionary Database Design, and 2 benchmarks from Oracle Online tutorials. And these benchmarks contain 9 transactions on average, and they have various kinds of structure changes, such as split or merge tables, move columns, denormalization. Our tool, Mediator, can successfully verify all the benchmarks in 12 seconds on average. To perform the second experiment, we also collected 11 real-world benchmarks from GitHub. These benchmarks are extracted from Ruby on Rails applications that have over 400 commits and have at least a structural schema change in the commit history. These benchmarks are quite large, and they contain about 105 transactions on average. And the evaluation result shows that the Mediator can successfully verify 10 out of 11 benchmarks. And it's quite efficient. It takes only about 47 seconds to verify each benchmark on average. We also, since Mediator wasn't able to verify one application, we manually inspect the reason and found the warning is actually a false positive. For that particular application, the bisimulation invariant inferred by Mediator was not strong enough to show the equivalence, but it's actually possible to find such bisimulation invariant to prove the equivalence. So to conclude, here are the main contributions of this work. First, we have introduced an equivalence verification problem between database-driven applications with different schemas. And second, we have developed a sound and relatively complete proof methodology for equivalence checking in this context. And third, we have showed how to automatically verify the equivalence using off-the-shelf SMT solvers. In general, I think this work lies in an exciting area at the intersection of programming languages and databases communities. And I believe this area would provide lots of opportunities for new research. With that, I'm happy to answer questions.
So in the definition of equivalence between programs there, it used sequential composition of updates followed by a query, so which means that you're not considering concurrent.
Wait, say it again.
I
consider concurrency?
So the definition of equivalence was a sequence of updates followed by a query. So there's no concurrency.
No, we don't
the
consider.
updates. So I was wondering, does that mean that can you model refactorings where one transaction in the original is mapped to 2 transactions?
For that one, we require the user to manually specify the mapping. But if you want to automatically do that, we can also iterate all the possible mappings so that if we can find one, then that means it's successfully verified. Otherwise, we cannot verify.
Okay.
Yeah.
And this doesn't produce any concurrency problems, the fact that there's more potential?
No, I don't think so.
Okay.
Okay.
Right. Thank you.
So I was wondering whether I could interpret your results as really that database applications can be treated as essentially like abstract data types being refined or being shown equivalent, where you just kind of think of the program as working over an abstract data type, which is a database now, and just transforming, and you're proving how we would typically prove, an abstract data type being refined to another one. Is that an intuition one can take back? Is that?
So the question is it similar to the database application is similar to the abstract data type?
It's just like some data that the program is operating on.
Yeah, in some sense they are similar. For abstract data type, you also have some sort of operations to operate on the data structure. And here is the...
I'm thinking of the spec as the old one and the program as the new one.
Right, but the difficulty, but there are some other challenges here because the underlying program is actually a SQL program, so there may be some problem with the logic to assert the property.
So there are some Slido questions that quite a few books. So the first question is, can you just simply transform the queries to relational algebra formulas and then prove them equivalent?
No, actually, the equivalence definition here is a behavioral equivalence. So it considers not only the query, but also the update. So the definition says that no matter what updates you do, if you do same query, you can get the same result. It's a little bit weaker than the than the work on proving the equivalence of two queries, because you may have different updates before the query to make the states of the database into totally different states. So it's a harder problem than the equivalence of query equivalence.
Okay, so one more, actually a couple more questions. So someone is asking, how many queries are needed to make sure two databases are equivalent, and how do you choose which types of queries?
Wait, say it again. How many queries?
Right, how many queries are needed to make sure two databases are equivalent?
Well, the queries are actually because as a programmer, you write some sort of queries in the program. That means the queries we are considering are all the queries that the programmer writes in the program. So it's not a fixed number. It's dependent on the program itself.
Okay, great. Now the third question is, how common are structural schema changes in practice?
For that question, I actually have some sort of statistic. I think in the paper we did a simple empirical study to investigate various kinds of schema changes, and it turns out that the structural, we actually investigated 100 Ruby on Rails applications, and there were 44 applications that have this kind of structural schema changes.